So I'm doing this as the third equation of motion, and this one actually isn't on the formula and data booklet for AQA. But I think in terms of symmetry and in terms of completeness, it's one that I think is worth doing just so you're aware it's there. Because you may be using older resources that refer to it, or it could be as one of the questions where you have to do something novel or you're given some context. You may be given some information that allows you to work this out. Anyway, I just think it makes sense. So similar to the S equals ut plus half at squared equation, I'm going to just express that as at is v minus u. So that's us defining what acceleration is. So then, same idea. I'm going to keep the graph simple. So velocity is a function of time, and then we've got time, and then we've got a changing speed from u to v as time increases. And we've done a number of different methods. So the trapezium rule, average velocity multiplied by time. We've done splitting this into a ut displacement and then adding on this extra triangle. But you can probably see there's another way of doing it. We could work out the size of this rectangle and then subtract this area. And this area is actually the same area as this one. So we should end up with, rather than adding on a half at squared, we should subtract a half at squared. So we'll see that in a second. So looking at this, we've got that S equals VT, so this larger rectangle, but then I've got slightly too much, and I need to take away this area. And this distance from V to U is V minus U. So I need to subtract that. So subtract a half, because it's a triangle, V minus U multiplied by T. And again, it's starting to look familiar if you've used this equation before. It looks a little bit familiar, but not quite right yet. But then we just do that substitution again where V minus U is AT. So S equals VT minus a half AT multiplied by T, which is S equals VT minus a half AT squared.